I will get that if I simply take k equals 1 and e. So e to the minus at has the Laplace transform 1 over s plus. Okay, so that formula encompasses in it a lot of important special cases. The next thing in the formula is what gives us the utility of the Laplace transform. If I have the derivative of a function and so let's say I have the derivative of a function. The Laplace transform, the derivative of the function, you can show it's going to be s times the Laplace transform of the function itself. If it has a bar on top, that means Laplace transform, function of s, minus the actual function putting at t equals 0. So that is the actual function evaluated at t equals 0.
Can you give an example of that last one?
Yeah. We're going to be using it, so I cannot take the time now. All you need to understand is a dictionary of your derivative of a function on one side, the other side is s times the Laplace transform of the function, whatever it is.
Oh, okay.
It's just
Okay.
dictionary.
I got it.
I'm not doing any derivations or anything. Opposite there is the integral. I have integral from 0 to t, and here is definite integral, so it's a dummy variable here, so I use let's say r. This involves, the real involves multiplication with s plus this extra term. Integral involves division by s. So that's f power of s divided by s. Next, the next one is a tricky one. That's going to be also very important. If you have a function that is defined as follows, and I guess I'll change what I have in the notes. I think we can get it. So let's say I have a function of t that is defined as 0 for time less than d, h at t minus d for time greater or equal to d. So this needs a little bit of explanation. So you have a function where t appears as t minus d. Okay, what does that look like? The delay. That's going to be playing the role of delay. Now, we're interested at all positive values of f of t. So even though for times between 0 and d, and here if you want to be more precise, since only positive times affect, between 0 and d, even though the argument here is negative, the argument of f is still positive. So this is specification. I have a function that for a duration d is 0. So here is f of t, here is time, this time is 0. The Laplace transform is only affected by what happens at positive time. So from time 0 until d, this function is 0. And then it's h of t minus d. So what is h of t minus d? If this is h of t, h of t minus d, remember when we're talking about the delay, it's shifted by d to the right. So this particular construct has Laplace transform. The Laplace transform function without the delay times e to the minus d times s. So I have the function of t, which is defined as 0 for the interval 0 to d. And for time greater than d, it's another function h of t delayed by d2. So this is the orange curve as Laplace transform, the Laplace h bar of s, that's the Laplace transform of h of t without the delay. Finally, later on we'll have usefulness for two special ones. This I don't have in my typed notes, in my posted notes, but I'm adding them. E to the minus at times sine of omega t as Laplace transform omega over s plus a squared plus omega squared, and e to the minus at cosine omega t is s plus a over the same denominator. That's the dictionary. Except for the last two entries, they are on APC 3, page 5. For your exams, the way I make the exams, they're closed book, but I'm allowing some sheets of handwritten notes. In addition, I'm providing the dictionary in exam.
What calculator? Calculator? No.
Maybe not. I haven't made the exam yet.
For the transform, the integral from 0 to t f bar, is that f bar s the transform of the f of bar, or f?
Yes.
Okay.
Yes.
Okay.
F bar is the transform of f of t. Okay?
Wait.
F of t with Laplace transform is f bar of s. Mika.
For the transformation of the delay, is that e to the power of negative ds?
Yes.
The x component?
E to the minus ds. That's all.
Oh.
S is not that.
Yeah, that's the s variable that I have in the Laplace transform. Okay? Megan.
What page or book are you talking about?
Page 5 of APC 3 of the notes.
Oh, okay. You said book, so I was like, sorry.
Is that booked?
Yeah.
Okay. Oh, the posted notes. Okay. Everybody clear? There's another thing that we'll be using in the Laplace transform in addition to the dictionary. One last thing, and then we'll start with the example. And the last thing, something very useful, is going to be the final value theorem. I guess all right. All right. If the limit as time goes to infinity of a function of time exists, in other words, if it's not the sine, etc., this is going to be equal to, it is We'll be using this a lot, really a lot. Why is limit as t goes to infinity important? Hold on.
That's when it reaches steady state.
Exactly. That gives us steady state values. And there are two ways you can go to steady state values. You can use the dictionary to go from Greek to English and partial fractions, expansions, and so on, and do a lot of work. And then after you have the function of time, take the limit as time goes to infinity. Or you can simply use the final value. Notice it says, if the limit exists. The purpose is really the reverse. I have f bar of s. Without doing a lot of work, I want to find the new steady state value. How can you figure out if that limit exists when all you have is the Laplace transform? The answer is limit exists if f bar of s has no positive denominator roots and no more than one denominator root with 0 real part. That's when the limit exists. So if you want something specific, so you know, hey, I have a final value. That's the rule. So if I have f bar of s equals s plus 2 over s plus 5 squared s plus 7, final value theorem applies. If I have this, there's one denominator root at 0, just one applies. If I have this, it doesn't apply. If I have doesn't apply. This has a coupler's conjugate denominator roots at plus or minus 2i. That's 0 real part. So you wouldn't apply for that.
You're going too fast.
Riyam, sorry.
You're going too fast.
Yeah, can you show us that last, the one before?
Okay, well, I'm just explaining that f bar of s, so if the limit exists, I can find the limit as time goes to infinity of a function from the Laplace transform without first inverting. You simply take limit as s goes to 0 of s times f bar of s. The question is, when does that limit exist? And it exists if f bar of s has no positive denominator root. First of all, you have even one positive denominator root, it doesn't exist. You can have a single denominator root at 0. But if you have a pair of denominator roots with 0 real part, it doesn't exist. So at most you can have, your denominator roots should all be negative, or you can have 1 at 0. Anything else, the limit doesn't exist. That's what it boils down. Simple as that. So this, I haven't seen any book, but that's the fact. Boils down.
Just small question, why it's 5 plus 7? Is it 5 plus 7?
S plus 7, does it? S plus, just as an example. So this one wouldn't have, it wouldn't apply because it has denominator root at minus 7, that's okay. But this has roots at s equals plus or minus 2i. Both have 0 real part. So this has a pair of roots with 0 real part. And therefore the limit doesn't exist. Okay. In this case, I mean, you can see from the dictionary, it's this case without the a here, okay? And you would have repeating sine or cosine, which does have the limit as time goes to infinity. All right. The power of the Laplace transform is this particular entry. So let's go ahead and spend at least the 4 minutes I have left in setting up the example. Okay? So we can continue on that on Wednesday. And I'm thinking of not making the homework due yet. I want to have covered Laplace transform, so I can tell you the homework will be due Wednesday next week, okay? Not Monday next week. Homework 3 will be due Wednesday next week. I'll finish it. All right, so let's look at this example. So let's go through the first 3 steps. Okay? So, what do I have? Constant volume is not a variable, one-way reaction, only reactant CA. And there's the reaction, I don't have to consider B. So, step 1, the model is ddt of V times CA equals F CAF coming in minus F CA leaving minus V K CA. Which V is constant, and pull it out and divide by it. So I get that dCA dt equals F over V times CA free minus F over V times CA minus K CA certificate. The measurement equation is given to you that I have a delay of 5 minutes. So Y of t is simply I'm giving you the concentration of A with a delay of 5 minutes. That's it. So our material balance is simply on A, rate of accumulation derivative, flow in times CF, flow in is equal to flow out, it's constant volume, minus FCA. I should say some constant density. Constant density. Add constant density. So the mass balance gives us F equals F out. Okay? So that's step 1. Any questions? Let's quickly do step 2, and then we're going to stop after. Well, ideally, I would like to stop after we linearized, but only for 1 minute. So, nominal steady state, you're given that under normal operations, we have 90% conversion. So 90% conversion and CAF naught equal 0.2 moles per liter means that CA naught will be 10% of that left. In other words, 0.02 moles per liter. And we know CAF naught. And what is unknown? Which variable is unknown? What is manipulated? The flow rate, right? So F naught is the only thing unknown. So at steady state, what do we have? So steady state version of the model is going to be 0 equals F naught. Volume is a parameter given at 100.